Class, this is Dr. Selby here, and today I want to solve a sample gas law problem. Here we're given initial pressure of 1.8 atm and an initial temperature of 25 degrees Celsius. We're going to heat the sample and the temperature increases to 350 degrees Celsius. And we're looking for a final pressure in units of atm. So the first step here in ideal gas law problems is always convert temperatures in the problem to Kelvin, because the Kelvin scale is an absolute scale and the Celsius scale is not. So I'm going to do a baby step before I get going with the rest of the problem. So we're given an initial condition, or a T1 equals 25.0 degrees C, and to get to Kelvin we add on 273.15, and that equals 298.15 unit Kelvin. I'm going to do the same thing for the final temperature, T2, and that equals 350 degrees Celsius plus 273.15, and that is equal to 623.15 unit Kelvin. Okay, so that was a baby step dealing with temperature, because it is a must in these problems that in solving the problems, you always are dealing with Kelvin. Okay, we got that taken care of. Now I have this equation here, PV equals nRT. That's the ideal gas law. And these are all the variables. P is pressure, V is volume, N is number of moles, R is the gas constant, and T is temperature, always in Kelvin. And so I'm only remembered this one law, and I derived for the situation this law to solve my problem. So what do? Well, here we're changing pressure and temperature. So we're going from condition 1 to condition 2. And that means that our volume is constant. So it's a sealed can. That makes sense that volume is constant. It's a sealed can, so the numbers of moles is constant. And our gas constant is just a constant. So what I want to do is manipulate this to get all the constants on one side of the equation and get my variables on the other side. So I want pressure and temperature on one side, and I want number of moles, R, and volume on the other side. So to do that, I'm just going to rewrite this here. PV equals nRT. And I am going to divide both sides by my temperature. So that gets temperature on the left-hand side. And I want to get rid of volume. So I'm also going to divide both sides of volume and then cancel. So volumes cancel here. Temperatures cancel here. And what we're left with is pressure on temperature equals NR divided by our volume. And remember, in this problem, this is a constant. What that means is no matter what we do to this system, is that the ratio of pressure to temperature is going to remain constant. And so that means I can rewrite this for an initial and final condition as P1 on T1 equals P2 on T2, since that ratio does not change. In this problem, we're asked for the final pressure. That's our P2. So I want to isolate the variable P2. What I'm going to do is just multiply both sides by T2 to get rid of it. And this cancels. And so we're left with P2 equals T2 times P1 divided by T1. And then we just plug in the values. So this equals, our T2 is 623.15 Kelvin. Our P1 is 1.8 atm, 1.80 atm. And then we divide by our T1, which is 298.15 in unit Kelvin. We see that our unit kelvins cancel. We're left with ATM, which makes sense for pressure. And our P2 equals, after rounding to three significant figures, 3.76 ATM. That's the end of this presentation. I hope this was helpful. Thank you and have a great day.